Dr. Mitchell, would you turn the sensitivity on your... Sorry, Dr.
Yeah, well, sorry, what was the question though?
Would you turn the sensitivity on the mic up?
Is this better?
If you could turn it up a little more, that would be helpful.
All right, that's a maximum now. Share desktop. Okay, so how's this? Can you see my desktop now? And you can hear me okay?
Yeah.
Okay, well, let's get started. So I'll try to get better with my handwriting as the course progresses, but this is probably likely to still be terrible. All right, so today we're really going to start with the mechanics, and so we're going to call this Chapter 1. And it's going to be an introduction so that we understand the material that we're going to cover in the coming weeks. Okay? So the first thing is analytic versus vector mechanics. So most of you have already been exposed to some analytic mechanics, and I hope that all of you have been exposed to vector mechanics. So vector mechanics is Newton's second law. So basically, you can figure any classical system you can describe with this simple equation, which we all know as Newton's second law. Now, I say it's a simple equation, but it's actually not that easy to work with in complicated situations, right? In Cartesian coordinates, this is actually three equations, right? So for example, it's true for each component of the vectors, right? So fx equals to max, right? And furthermore, this is actually a differential equation, right? This is really f of x equals m times d squared x by dt squared, right? So this one equation in Cartesian coordinates is already 3 second-order differential equations. And so as it turns out in Cartesian coordinates, it's usually fairly straightforward to implement. But vector mechanics can be very difficult to implement in more complicated systems. So vector mechanics, not always straightforward to implement. So for example, you wanted to describe motion on a sphere, it's not going to be very convenient. Because you'd have to do that in polar coordinates. So analytic mechanics is a completely different approach. So there's no vectors. Instead, we use a scalar quantity to describe a system. And then we use differential equations that are based on that scalar quantity to describe the evolution of the system. So we can obtain differential equations from the scalar quantity. To get what we call the equations of motion. And I'll just write that EOM in the future. Okay? H2. So what do we want from a theory of classical mechanics? Oh, it changed color all of a sudden. Well, we want to be able to describe the system. What does it mean to describe a system, and what does a system mean? So for a system, for example, we can think of n particles that are subject to forces and have positions and velocities. And so by describe, we want to be able to know the position and velocity of these particles. At all times. So you cannot hear me talk at all now? I could just notice the So anybody can hear me, or is this better? Well, Alex says that School of Mines can hear me. I don't have the DDM here, so. Are you sure it's not a connection issue? Why does this thing go down by itself? So USB, you cannot hear me, Jimmy, at all? Maybe it's your internet connections. Well, I'll just keep going, and then it will be on YouTube, and then we'll figure it out next Monday how to do it better. Okay. So, for a theory of classical mechanics, the goal is to describe a system where the system means the number of particles, and describe means we want to know the position and velocity of those particles at all times. And so, the evolution of the system is determined by the initial position and velocities of the particles, and the forces or potential energies that exist, that act on the system. So what we'll find is, so Newton's laws you've had practice with, and you know that they allow you to describe the evolution of a system, right? If you know the initial position and velocities of, say, a cannonball, and you know the forces that act on the cannonball, you can predict the path of that cannonball. And if you know the position and velocity at one point, you can predict that path both in the future and in the past. And so what we're going to talk about during this course is an alternative way to Newton's laws of doing this that's much more powerful representation of classical mechanics, and that's what we call analytic mechanics. So we'll do an example of Newton's laws, and I'll start it for you, and then we will you will finish it in the assignment. So that's just to demonstrate how annoying some problems can be with Newton's laws. So let's do an example of solving a problem with Newton's laws that we'll find later in the course is very, very easy to solve with this new analytic mechanics framework. But we'll start it off here in the more complicated way using Newton's laws. So this is called the compound pendulum. So a compound pendulum you have a normal pendulum, and then you have a second pendulum just attached to that one. So it's a pendulum on a pendulum. Okay? And we can give these two masses, different masses, M1 and M2. So what we want to is describe the motion of M1 and M2. Okay? And we'll do it here using Newton's laws. So hopefully this is trivial for you guys. This is, first year undergraduate physics, how to solve for the motion of these pendulums. But I'll get you started here, and you can finish it in the assignment. So the first step is to draw a diagram. which we did. The second step is to draw a coordinate system. So let's put the origin here. And what we want to do, of course, is we want to describe the motion of the two masses. That means we want to know x1 of t, y1 of t, so that's the x and y position of the first mass, x2 of t, and y2 of t for the second mass. So what we need are the equations of motion for xi of t, where I is 1 or 2, and yi of t. And that's our goal. And we know that Newton's laws can give those to us, right? So the second step in using Newton's laws is to draw the forces. Let's try with a red pen. So on the first mass, we have the tension here, which I'll call T1, and we have its weight, M1G, and then we have the tension from the second string, T2. And on the second mass, we have its weight, M2G, and we have an equal and opposite, T2, right? So if we write Newton's law for these guys, we have M1 A1 is equal to T1 vector plus T2 vector plus M1, G vector. And for the second mass, we have M2 A2 equals T2 vector plus M2G. Okay? So this is really 4 equations, right? Since it's true for x and y, right? And so that gives you equations, differential equations for x1, y1, x2, y2. Now, we also have what we call our constraints. So if we ask ourselves, how many unknowns do we have? We have x, y, or x1, y1, x2, y2. That's 4 unknowns. And we also don't know t1 and t2. So we actually have 6 unknowns. So we only have 4 equations and 6 unknowns, right? So it is in fact possible to solve this problem, even though there's only 4 equations and 6 unknowns. That's because there's 2 additional equations that tell us that the motion of the 2 masses must be perpendicular to the string, right? If it's a pendulum. And so what that tells us is that the acceleration, so we get 2 more equations. But the acceleration is perpendicular to the strings. Or they could be massless rods if you prefer. And so from that, we get the 2 more equations. Now it's easier if we introduce some angles because x and y are quickly going to become annoying. So let me call this angle here theta. and this angle here, phi. So those two equations that we get from the constraints are, so we're just equating the component of M1G that's parallel to T1 plus the component of T2 that's parallel to T1 is equal to T1, right? So we have M1G cos theta plus T2 cos phi cos theta equals T1. And for the second one, we have M2G cos phi equals T2. And if we give these rods length, which we'll call L1 for this one and L2 for this one, this theta and phi, right? Well, I guess I shouldn't put a dot on it. Theta and phi are also unknowns, but they're not really unknowns because you can express them in terms of x and y. And so cos theta, that's terrible writing. Cos theta is given by x1 over L, and cos phi is equal to x2 minus x1 plus L1 over L2. I believe that's correct. So in principle now, you can take these two, right, and put them into this constraint equations. So now these are equations in terms of x's and y's. And then you can eliminate, well then you have 6 equations, 6 unknowns with the T1s, T2s, and all the x and y's. And so now it's just a matter of math to get a series of differential equations of the form. Right. And that'll be the problem for assignment 1. Any questions so far, if you can hear me? I don't know why the volume keeps going down. Automatic. All right, so now let's continue with our introduction to analytic mechanics, and pretty much the rest of the lecture is going to be a bunch of definitions. So a particle is a point mass. So it has no intrinsic dimension, but it has a mass, m. The position vector we will denote by r, and it has 3 components. For example, Rx, Ry. The velocity of a particle is the time derivative of the position vector. And so it also has 3 components. the acceleration, which we won't need in analytic mechanics, or sorry about that. Looks like it was my turn to lose the internet connection. Can you guys hear me? All right. All right. I don't know what that was about. All right. Hopefully this does not persist with this kind of quality. All right. So if everybody can hear me, I'll resume. Hopefully the YouTube video is reasonable. So I was just going through the definitions, right? So a particle is a point mass. We want to know its position, its velocity, and its acceleration. And so in general, if we want to describe the motion of a particle, what we need are the equations of motion. And what the equations of motion do is they give us the position of the particle as a function of time. And that's in general what we want to know, right? And so for example, as we saw, Newton's second law gives us exactly those equations, differential equations of motion. So equations of motion are not necessarily R of t equals something. The equations of motion can be differential. We still call that the equation of motion. I mean, you don't have to solve the differential equation to call it the equation of motion. Okay? So I'm just going to introduce a little bit of notation here because we're going to have a lot of d by dt's. And so we're going to introduce a new notation for derivatives. We're going to put a dot over things to mean d by dt. So when I write x dot, I mean dx by dt. And of course, it's implied that x is a function of t, right? So similarly, you can do that with a vector. R dot is just dr vector plus 3 equal signs by dt, okay? That's just a notation. And so, for example, acceleration, we can just note as r double dot. Okay? That'll make our life much simpler. So another thing that might come up is a rigid body. And a rigid body, so it's not like a point, like a particle. A particle is a point mass, right? It has no intrinsic dimension. A rigid body has a dimension, right? So it's an ensemble of particles that are whose relative positions are fixed with respect to each other. Fixed relative positions. And so in general, to describe a rigid body, so in Cartesian coordinates for a particle, right, you only need 3 numbers to describe its position, right? Like it's Rx, Ry, and Rz. For a rigid body, you need, for example, in Cartesian coordinates, 3 coordinates for the center of mass of the rigid body, and then 3 angles to describe its rotation, its orientation. So that's the key thing. For a particle, it only takes 3 numbers to describe its position, whereas for a rigid body, it takes 6. 3 for the coordinates of, for example, the center of mass, or one of the ends of it, and then 3 angles to describe the orientation. And so that brings us to the point of, I guess I can't count, so it's 1, 2, 3, 4, 5. That brings us to the point of degrees of freedom. And it's a very important concept in classical mechanics. The degrees of freedom is the minimum number of scalar quantities that you need to describe a system. The minimum number of scalar quantities needed to describe the system. So for a given system, we say it has a certain number of degrees of freedom. So for example, one particle in space, so I'm going to call the number of the degrees of freedom n. Okay? So n equals 3. We have 2 particles in space. To describe the position of those 2 particles, we need 6 numbers, right? The x, y, z coordinates of both particles. A rigid body and is also 6, right? We need the 3 quantities to describe the position of, say, the center of mass or some other point on the rigid body, and 3 angles to describe the orientation of the body. Well, I think that's pretty obvious now. I think I don't need to make more examples. You know, 1 rigid body and 1 particle is 9, etc. Okay. And so, formally, a system, I guess we already described that, is an ensemble of particles and rigid bodies. And so, for a system, the system itself can have degrees of freedom. So you have to think of, when you talk about degrees of freedom in classical mechanics, you don't want to think so much of the individual things that make up the system, but rather what is the total number of numbers that you need to describe the whole system. Okay, so we'll find in classical mechanics, for example, that we might be describing 2 particles with 6 degrees of freedom, but we might find that the 3 coordinates of each particle are not the best degrees of freedom to use. And so we might use some Newtonianly speaking, strange coordinates to describe the system. For example, if we have 2 particles, we might find it more convenient to describe them by the position of their center of mass and then their relative position to the center of mass. Because we may find that the equations of motion simplify with a good choice of the quantities that you use for degrees of freedom. The next thing we need to know are constraints. there are various types of constraints, and what they typically do is they change the number of degrees of freedom. So let's do an example. If we have two particles, let's call this particle M1 and particle M2, that are connected by a rigid rod. The question is, how many degrees of freedom do we have? Well, in principle, we have 6 degrees of freedom, right? We have two particles. So we have x1, y1, z1, and x2, y2, and z2, right? However, we also have, we'll use k for the number of constraints. And so the constraint is that these two particles are in fact connected by a rigid rod of length L. So we can write that as an equation where we can say that x2 minus x1 squared, so the distance between the two particles, was y2 minus y1 squared plus z2 minus z1 squared is equal to L squared, right? And so what this means is, it's a little bit of an ugly equation, but you can in principle express x1 in terms of the other coordinates, right? And then L. So the 6 coordinates are not independent. And what that means, of course, the definition of degrees of freedom is the minimum number of coordinates that you use to describe a system. And here we know that we can use 5 coordinates to express the 6th coordinate. So in fact, the number of degrees of freedom, numbers of degrees of freedom, is equal to 6 minus 1, and so it's equal to 5. So that's the number of particles minus the number of constraint equations. So now we have to change what we mean by n, right? So in the future, we'll use capital N for the number of particles, and we'll use little n for the numbers of degrees of freedom. So what we really have here is that should be n, and then this is n, little n. Okay? So here's another example. Let's say we have 4 masses. what does n equal to? So we have 4 masses, and they're all connected by rigid rods. I guess in the notes I have different lengths, but that's not going to matter. So what is the number of degrees of freedom? Well, first we need to find out how many constraint equations. And it's very easy to see that the constraint equation, you get one constraint equation per rod, right? So the distance from this one to this one is constrained to be a certain length. The distance between this and this is a certain length, this and this is a certain length, and this is a certain length. So you can get four constraint equations. I'm sorry, n is the number of particles. So this is not actually n, right? This is 3 times n. So for a free particle, so each of these particles has 3 degrees of freedom, right? So with no constraints, the number of degrees of freedom would be 12. Right, that's 3 times n. And then it's minus the 4 constraint equation. And so in 3-dimensional space, there are only 8 degrees of freedom to describe these 4 particles. In 2D, let's say that these 4 particles are constrained to the xy plane. You can either start off with 2 times n minus 4 to get 8 degrees of freedom, or you can add in 4 more constraint equations of the type zi equals 0, so they're constrained to the xy plane. And so no matter what you do, you will get that n equals 4 degrees of freedom for this system. So that's if they're constrained to xy plane. Okay? And so in general, for n particles and m rigid bodies, the number and k constraint equations the number of degrees of freedom is 3 times the number of particles, because it takes 3 coordinates for each particle, takes 6 coordinates for a rigid body, and then minus the number of constraints. Okay. So now there are different types of constraints. Types of constraints. So the first type of constraint is what we call holonomic. So a holonomic constraint is basically the good kind of constraint that are easy to deal with, and most of our problems will have holonomic constraints. What holonomic constraint means is that their constraint equations involve only coordinates. So the constraint equations involve only coordinates. So for example, the rigid rod that we just did is a holonomic constraint. Here's a less obvious holonomic constraint. Another example. Rolling without slipping in one dimension. So that's the case of a circular object. Oops. It looks more like a circle. So we have a circular object here that's rolling without slipping, right? So let's call this the x direction. And so we have a choice here of how to describe the position of this rolling disk or sphere or whatever it is. We can choose as a degree of freedom. There's only one degree of freedom, right? And we can use x or phi. But in principle, ahead of time, we don't know. If it was rolling with slipping, then it has 2 degrees of freedom. It has the position of the center mass and the rotation of the thing. So somehow you can go from these 2 degrees of freedom, the position of the center mass and the rotation, to 1 degree of freedom. So that means that there's a constraint equation that brings those 2 degrees of freedom down to 1. So what is the constraint equation for rolling without slipping? Well, the constraint equation for rolling without slipping is that the point of contact here is instantaneously at rest, right? That's what rolling without slipping means. So if the thing is moving with a velocity VCM, so velocity of the center mass, the constraint of rolling without slipping is that VCM is equal to R phi dot. Remember, phi dot is d phi by dt. Sometimes we call it omega, right? So the speed of this point here being 0 means that VCM equals R times phi dot. That is, if we write it again as x dot equals R phi dot. That is not a priori a holonomic constraint, right? This includes velocities not coordinates. Remember, the definition of a holonomic constraint is it's a constraint equation involving the coordinates. And here, the equation of rolling without slipping is a constraint equation that involves the velocities. So a priori, this is not a holonomic constraint. However, we can integrate this non-holonomic constraint to obtain a holonomic constraint. So to really be explicit, right, we have dx by dt equals R times d phi by dt. R is a constant, right? And so we can trivially integrate both of these equations to get x equals R times phi, and in principle plus a constant. This, remember the 2 coordinates are x and phi. This is now an equation that is holonomic. That is, the constraint equation is in terms of the coordinates. That means we can eliminate one of the coordinates for one of the other coordinates in all the equations of motion. And this only works in one dimension. Okay? So then the obvious next type of constraint is a non-holonomic constraint. So a non-holonomic constraint, of course, is a constraint that is non-holonomic. So it can either not an equation of the coordinates, or it could be an equation involving the coordinates but containing inequalities. So for example, a non-holonomic constraint is particles constrained to a volume. So let's say, for example, you have a sphere. I'll get better at drawing. And you have a bunch of particles in here. So you can think of the particles as being a gas. But they are limited to being inside the volume. So it is an equation of their coordinates, but it's an inequality. And the equation, if we put the origin here, for example, at the center of the sphere, the constraint equation is that the position vector of each particle, that's an I there, has to be less than R. So this is an equation of the coordinates of the particles, right? It relates the coordinates of the particles to another number, but it's an inequality. And so that is not a holonomic constraint. The other example of a non-holonomic constraint, this is going to be horrible to draw, is two-dimensional rolling without slipping. So in two-dimensional rolling without slipping, so you might have to look in the notes for a decent diagram here, but I'll try my best. So this is the XY plane. Let's say we have a sphere. And we have a point of contact here. And let's say the sphere is instantaneously moving along a vector ds. So the sphere is rotating. So it's rolling without slipping, right? And so instantaneously, that's a phi. All right, we have that the speed of the sphere, so the VCM, that's ds by dt, and that's got to be equal to r times phi dot. And let's say this, the sphere, if I look from above, it's going in a direction theta. Remember, the coordinate of the sphere now is x, y, and the rotation angle phi. So we want to express, find an equation of constraint that relates the coordinates so we can have less coordinates and thus less degrees of freedom. The problem is that it's not possible to integrate this equation to get an equation between x, y, and phi dot. Because dx is given by ds times cos theta, just from this diagram here, right? That's dx. That's dy. So dy is ds sine theta. And it's not possible. So if we use this equation here, so that's rolling without slipping, right? When we try to get ds or dx in terms of d phi, the best we can do is dx equals r cos theta d phi, and dy equals r sine theta d phi. You cannot get from this x equals something that depends on phi. So you can't integrate these equations simultaneously because they're independent. And so you cannot reduce the number of degrees of freedom for a sphere rolling in 2D. Okay, so that's a non-holonomic constraint. So it's a special case in 1D, right, that you only have this one dimension, and so you can immediately integrate the differential of one coordinate to get it in terms of the other coordinate. As soon as you have 3, at least this non-holonomic constraint of rolling without slipping does not allow you to eliminate one of the variables. Okay, so it's very important to understand what types of constraint you have and whether they help you reduce the number of degrees of freedom. We have about 10 minutes left. So the next type of constraint is called scleronomous. Scleronomous. And that's a constraint. It can be holonomic or non-holonomic. Okay. This is a constraint that does not depend explicitly on time. What does that mean? Does not depend explicitly on time. We're going to use that term a lot. What that means is that if you take the partial derivative of the constraint equation, if you take the partial derivative of the constraint equation with respect to time, you get 0. That's what scleronomous means. All right, so for example, what was our constraint equation? This was the constraint equation for 2 particles connected by a rigid rod. If you take the partial derivative of this with respect to time, because time doesn't appear explicitly, then you get 0. So this is a scleronomous constraint. Okay? So the x's and y's, if these two things are moving, x and y do depend on time, right? But there's no explicit time dependence in the equation, so the partial derivative with respect to t is 0, not the total derivative. Okay? So be careful, that's partial derivative. And so then, of course, is the opposite of the scleronomous constraint, and that's called rheonomous. And that just means that d by dt of the constraint equation not equal to 0. Okay? So let me take another 5 minutes and then introduce generalized coordinates, and then I guess we'll stop there for today. So generalized coordinates are the coordinates that we use in the framework of analytic mechanics. So when you have a system, in general, one can choose the coordinates to describe it. So it's up to you. For example, maybe you want to use Cartesian coordinates. Maybe you want to use polar coordinates. Or maybe you want to use something more exotic. Right? You have a choice of which coordinates to choose. And in sometimes it makes more sense to use one type of coordinates than the other. For example, if we go back to our double pendulum here, so I told you that there's 4 coordinates, x, y, for both of these particles, but there's also 2 constraints, right? There's the constraints that, the distance from this particle to the pivot point is a fixed length, and the constraint that this particle and this particle are separated by L2. And so really, there's only 2 degrees of freedom in the compound pendulum. So maybe describing the compound pendulum with these 4 coordinates is not the smartest choice. In fact, a smarter choice is to use only 2 coordinates. And of course, you can use whichever ones you want because they're all related. But a clever choice, of course, to use the angles theta and phi. So by specifying theta and phi for the system, you've completely described it, right? And so generalized coordinates just means a choice of coordinates where the number of coordinates is equal to the number of degrees of freedom. Number of degrees of freedom. So in general, of course, we don't want to spend doing math for coordinates that we don't care about or that aren't necessary to describe a system. So we often want to find a set of generalized coordinates where the number of those coordinates is exactly the number of degrees of freedom that you need. So we often use the notation. So let's say, for example, that we have n particles. Well, actually, let's not say that they're free. Let's just say we have n particles. So that means the system is described by x1, y1, z1, all the way to xn, yn, zn, right? But maybe there are constraints. And let's say that there are k constraint equations. So in principle, there are only the number of degrees of freedom, of course, is 3n minus k. So that means that there ought to be a better choice of coordinates, which we call generalized coordinates, and there are only n of them. And so we usually use the notation that the generalized coordinates, we call them q's. So then we have q1, q2, all the way to q3n minus k. So one should be able to find the equations, we call the transformation equations, that relate the generalized coordinates to our initial coordinates. What's the function? So x1, the x coordinate of one of the n particles, can be expressed as a function of the q generalized coordinates, right? And similarly, down to Zn is also a function of the q generalized coordinates. So we can describe the whole system using only the q's, and if we need to be able to, after convert our description in terms of q's back to x's and y's and z's, we can use these transformation equations. So again, a trivial example was our compound pendulum, right, where we have the 4 x, y, and z's, or x and y's for both particles, the two generalized coordinates that we'll call theta and phi. One can easily write the transformation coordinates to get back x and y from theta and phi, right? So x1 is just L1 cos theta, y1 is L1 sine theta, etc. All right? But in theoretical mechanics, we're always going to do things a little bit more abstract. So I will always point you back to the example. So we have these generalized coordinates, and then of course, to describe a system, you need to describe both the position of the system and its velocity if you want to know its evolution. So we also have generalized velocities. So qi dot, of course, d qi by dt. And so the end goal will be to describe the system using the generalized coordinates and the generalized velocities. Of course, here I goes from 1 to n, where n is the number of degrees of freedom. So that was the last topic. Since we're run out of time, I'll start next Monday's lecture by a summary of this, and we'll do an example using generalized coordinates. So I apologize for the technology not being working super well today. I would suggest if you don't have a class next week before this class that you maybe try to log in 5 minutes early so we can deal with any tech issues ahead of time. Hopefully the YouTube lecture will be better. This is also my first time teaching a course like this, so I mean classical mechanics. But I hope it gets better in terms of my handwriting and all that. But please do follow along the notes and ask me if you have any questions. I'm very happy to respond to emails, and I respond very quickly. Okay, so if there are no questions, then I guess we'll stop there.